Hello and welcome back to another video of Turtles All the Way Down. Have you ever wondered how astronomers know how far away objects are in the universe? We've all been told that some stars and galaxies are unimaginably far away. But how do they know this? And what does unimaginably far away really mean? These are the questions we'll be exploring in this video. For most of human history, the sky's objects had remained eternal mysteries, as were their distances from us. These deep mysteries were understandably imbued with mystical and theological qualities. Up there were the realms of gods and goddesses, beasts of imagination, and powers beyond those of us weak mortals confined down here on the earth. There was very little we could ascertain about how far away celestial objects were. The little that we did know was that everything up there seemed to be at least farther away than the clouds, and probably much more so. We did know that the moon was the closest of the objects, as everything else, the sun, the stars, the planets, all could pass behind it. We also knew, through similar reasoning, that the sun was closer than the stars. However, there were points of light in the sky that seemed to move independently from the stars, and in sometimes erratic ways. In the Greek language, these were called planetas, or planets, meaning wanderers. Because of the vastly brighter sun, it was too hard to discern if these planets moved in front of or behind it. But it was assumed that the sun was closer than these wanderers. And so, for millennia, that was the extent of our knowledge of celestial distances. Over time, as our tools of science improved and our knowledge from them expanded, we began understanding that what we were seeing in the skies really followed rules that could be reasoned through. Astronomers and astrophysicists now have at their disposal a variety of methods that can be used as special yardsticks to measure the vast distances across the cosmos. Let's briefly discuss the units that are commonly used when measuring astronomical distances. Just as we may use a 1-foot ruler or a meter stick as our standard distance units, astronomers use a couple of standards as well. When we speak of distances within our solar system, which are relatively tiny distances when compared to those across the universe, we commonly use a standard distance called the Astronomical Unit, or AU for short. This is the average distance from the Sun to the Earth, about 93 million miles, or 150 million kilometers long. So the Sun is 1 AU away from us. Astronomers are not in unanimous agreement on what really defines the edge of our solar system. However, if we were to define it to be the swarm of comets that orbit the Sun at the farthest reaches, called the Oort cloud, then we can say the diameter of our solar system is about 2,000 to 200,000 AUs from end to end. As you can see, these units quickly become cumbersome to work with when speaking about distances vastly larger than these. At those reaches, our preferred unit is called the light year. A light year is the distance that light travels in 1 year. The light year is a little more than 63 AUs across. That is a distance of about 5.9 trillion miles, or 9.5 trillion kilometers long. 1 light year will take us about a quarter of the way to the nearest star, Proxima Centauri. Okay, so we've defined what these distance units are in space, but that still leaves open the question concerning this video. How do we know what the distances are to the planets, stars, and the galaxies? We obviously don't have astronomical unit or light-year-sized sticks that we can place in sequence out in space to measure distances between objects. So how is it done? There are a series of methods that overlap in their individual distance measures out to cosmic scales. Collectively, these are called the cosmic distance ladder. Each rung of the ladder represents a different method used for farther and farther distances away from us. The shortest distances from us are those measured in astronomical units, distances out to those objects within our solar system. These objects may be measured through the use of radar, where radio signals are transmitted out to the object, and the time it takes for the reflected signal to return can be used to calculate the distance. However, due to the weakness of the return signal and issues related to the motions of the measured object, the radar method only works for very close objects, such as the closest planets to the Earth, like Mars and Venus. The next rung out on the distance ladder uses a method called stellar parallax. This is related to viewing an object from different locations and comparing its apparent change in position against the farther background stars. This method can be demonstrated simply by holding out your finger and looking at it with one eye closed. Observe an object a little farther out from your finger. Now open your eye and close the opposite eye. Switch your eyes several times and you'll notice that the object appears to change position relative to the location of your finger when looked at from each eye. This is parallax. Each eye is a certain distance away from each other, and from each of their individual perspectives, the object seems shifted slightly in its location compared to the farther object. However, use the same method for very distant objects, like a finger a mile away, and you'll barely or not at all notice any change against its background. Stellar parallax works the same way, but our two eyes, in this case, are two different locations in Earth's orbit around the Sun. So if we view a star from one point of our orbit and view the star again from the opposite side of our orbit, say 6 months later, the star will appear slightly shifted in the sky relative to the background stars. It'll be shifted more so if the star is closer to us than if it were farther away. By using some trigonometry, we can calculate the distance out to that star. There is some overlap in distances used in this method and that used in the radar method. However, the stellar parallax becomes less useful with much farther stars, since they barely appear to shift positions. So, stellar parallax can work up to about 100 light years or so. There are tens of thousands of stars within that distance from us, where parallax can work well. The next methodological rung on the cosmic distance ladder is called main sequence fitting. This method makes use of a relationship between a star's luminosity or brightness and its temperature. This relationship is seen in a diagram called a Hertzsprung-Russell or HR diagram. On the horizontal axis is a star's surface temperature, and the vertical represents the luminosity as compared to the sun. That is, if the sun and the star were side by side, the luminosity of each is compared. Stars in various sizes, brightnesses, and ages can be positioned on the HR diagram. Most of a star's life cycle is spent moving along the middle portion of the diagram in a region called the main sequence. The other areas of the HR diagram, where the giant and dwarf stars are located, are where stars go when they are at the ends of their lives. So, how can we determine a star's distance based upon this diagram? Well, if we observe a star in the sky and accurately measure its luminosity and temperature, which can be done by examining its light spectrum, we can plot it on the HR diagram. But plotting a single point on the diagram will not yet give enough information about its distance. As you can see on the diagram, the main sequence consists of an arc of widely varying star brightnesses and temperatures. To get an accurate measure of distance, we need to plot many points to get a similar main sequence arc to compare to the ideal one. The best location in space for getting a variety of stars at different stages in their stellar life cycle and at similar distances from us are in star clusters. This is because all those cluster stars were formed from the same gas cloud. In other words, at about the same location in space. With a bunch of stars at generally the same average distance from us, we can plot many points on the HR diagram to form a main sequence arc. When we do that, we will get an arc, but one that is vertically displaced from the ideal main sequence, usually a little lower. This vertical difference represents a difference in luminosity, and therefore distance from us. The greater the brightness difference, the greater the distance from us. Just as a light bulb far from us will be dimmer than one that's closer, stars exhibit the same pattern. The main sequence fitting method can measure stars across our Milky Way galaxy and just barely out to the nearest galaxies, as long as individual stars can be made out. Our galaxy is 100,000 light years across. The nearest large galaxy to us is about 2.5 million light years away. That's the Andromeda Galaxy. Distances beyond our galaxy, in other words, extragalactic distances, must be measured using other methods. One is through analyzing special stars called Cepheid variables. These are stars that periodically change in their brightness over time. But what's fascinating about them is the fact that their periodicity is directly related to their brightness. The slower a Cepheid star's brightness changes, the brighter a star it is. These stars are what astronomers call standard candles. By that, they mean that every Cepheid that has the same periodicity will have exactly the same intrinsic brightness. They have a standard luminosity. It's like holding up several candles with identical brightnesses. If you know the standard brightness of one, you know what the brightness is of any one of the others. If they happened to be placed at different distances from you, you can simply work out the distances just based on the apparent brightnesses of each. This is exactly how Cepheid variables work. Cepheid variables can be seen out to distances of about 50 million light years. As mentioned, the nearest large galaxy to us is the Andromeda Galaxy, 2.5 million light years away. The collection of the nearest 25 galaxies to us is called the local group, and the diameter of this whole region of space is some 10 million light years across. So Cepheid variables can be made out beyond our local group of galaxies. Beyond the local group and out toward much farther galaxies, there are other methods that can be used to determine distances. Relationships between a galaxy's overall intrinsic brightness and its rotation rate have been worked out. This is called the Tully-Fisher relation, named after the astronomers who discovered it in the late 1970s. By measuring a galaxy's rate of rotation, we can determine its intrinsic or true brightness. The intrinsic brightness of a galaxy can be used as a standard candle in this case, and therefore its distance can be worked out. The Tully-Fisher relation deals with those galaxies that are rotating, such as spiral galaxies like our own. However, many, if not most, galaxies are not of this variety. They are of the elliptical variety. Those that are spherical, egg-shaped, or irregularly shaped need to be analyzed using a different but similar method. That's where the Faber-Jackson relation comes in. This method analyzes a galaxy's central star's velocities and that galaxy's brightness. There is a linear relationship between the two. The higher those central star velocities are, the brighter the galaxy is. This too, by analyzing the galaxy's brightness, can be used to determine the galaxy's distance from us. Okay, so there comes a point when galaxies are so incredibly far away that you can no longer make out their individual stars. What do you do then? There is yet another method that uses a standard candle, and these candles are some of the most brilliant phenomena in the entire universe. Supernovae, or exploding stars. But not all supernovae have a standard brightness associated with them. The explosive brightness will vary depending on their initial mass and other factors before their fiery deaths. However, there is one kind of supernova called the Type 1a supernova that does have a standard brightness for all of their kind. They all detonate with the same intrinsic brightness. A particular arrangement of a binary star system must take place first. A large star or a white dwarf and another white dwarf both must be in orbit around each other. The white dwarf's gravity pulls gaseous material off of its orbiting sibling star. This material will orbit and fall onto the dwarf star's surface, adding to its own mass. This accumulation of material continues. Once a threshold mass of the dwarf star is reached from all that piled-on star material, the dwarf star ignites and explodes into a Type 1a supernova. These explosions are so powerful that they can be seen at vast distances across the cosmos. Since these are standard candles, we know how bright they are supposed to be at various distances. However, supernovae, by their natures, are unpredictable events, so these flashes occur randomly across the universe at various distances and times. But if you observe one in a certain galaxy, then you can determine the distance to that galaxy. Distances that can be ascertained from Type 1a supernovae are about 1 billion light-years away. For perspective, the very farthest visible edge of our universe is about 46 billion light-years away. That's the radius of our observable universe. However, observing Type 1a supernovae out to 1 billion light-years seems to be quite inadequate to determine the much vaster distances beyond and out to the 46 billion light-year edges of our universe. How are those distances found? The last and highest rung on our cosmic distance ladder is by using a method analyzing the redshift of galaxies. We've talked about redshifting and blueshifting in our early videos on dark energy and on the beginning of the universe. Check them out here. The universe is expanding. On average, all groups of galaxies are moving away from each other, and in similar ways. The farther away a galaxy is from you, the faster it is receding away. And this observation is universal. That is to say, if you happen to be in another galaxy, in another part of our universe, you too would see most galaxies moving away from you as well, and at greater speeds the farther away they are. There is a direct relationship between a galaxy's speed away from you and the distance to that galaxy. This is called the Hubble law, named after Edwin Hubble, the astronomer who discovered the expansion of the universe. So, how do we determine the speed a galaxy is moving away from us? Through its light's redshifting. All light from stars and galaxies come from the nuclear burning of gases, like hydrogen and helium. The light that is given off, and that we can see, can be spread out into a rainbow light spectrum. Inside that spectrum are dark lines, called absorption lines. These lines represent the chemical elements within those astronomical objects. They serve as a kind of chemical fingerprint. But for our purposes, what's important about these lines is the fact that they all shift in position when the object is moving relative to us. So they'll all shift toward the blue end of the spectrum if the object is moving toward us, and they shift toward the red end if they are moving away from us. The amount of shifting determines how fast the object is moving. For example, if there happens to be a large redshift, then that object is moving away from us at a great speed. Most galaxies have a redshift in their spectrum, and the farther away they are, the more redshifting we see. Galaxies at the farthest distances from us, such as quasars, have the strongest redshifts known. The farthest galaxy that has been observed by redshifting, as of this video, is about 34 billion light-years away. Again, the observable edge of our universe is some 46 billion light-years away. Astonishingly, the farther we look out into space, the farther back in time we are seeing, because it takes light some time to get to our eyes when it was transmitted. So, by seeing galaxies close to the edge of the observable universe, we are actually observing the earliest formed galaxies. These are babies. Anything beyond that are proto-galaxies, or just clouds of primordial gas after the Big Bang. We've discussed several rungs on the cosmic distance ladder, but there are many others that are there. They are just not as commonly used as the ones we discussed, but there is a lot of overlap in their domains of use, and therefore each can be calibrated and adjusted so that distance measures can be more accurate. All of these various methods of cosmic distance measures agree with each other, and within reasonable error. The universe is all that we can see and experience, and it is an incredibly vast place. Unimaginable distances separate objects within it, and science has developed tools that have illuminated them. So the next time you look up into the night sky, think about how far away those objects are. Think how long ago that light was produced and all of the immense time that was spent traveling the cosmos to eventually be caught by your eyes. Thank you for staying with me, and turtles all the way down. I look forward to discussing the next big questions with you in upcoming videos. Stay tuned by subscribing to the channel. Until next time, stay safe and stay curious. Bye for now.